by basically evaluating that formula, by evaluating Gauss's law for the case of a wire just going along the z direction. But this is also a familiar geometry. It's one of the three simple cases that we talked about. And so, and I think we had some problems. I'm pretty sure we had some problems on this. So I'm saying it's a positive charge oriented in the z direction, unless we might as well let's draw an x and a y axis, and z is coming out at the top. And let's see, it says at a distance of 0.01 meters, the field is 5 times 10 to the fourth. So it says that the magnitude of the electric field, and how we put it, it's 0.01 meters. Equals 10 to the fourth volts per meter. Right? And in this situation, which way is the electric field pointing? Straight out, right? It's, if you put a positive test charge here, if you're out here, it always points straight out from the wire, right? Not up, not down, but in the xy plane. Right? And so, if you wanted to evaluate Gauss's law, you would draw a cylindrical surface around this thing, and you would note that everywhere on the surface, the electric field is always pointing out exactly normal to your cylinder, and therefore, when you integrated E dot dA around this thing, and you also note that the end caps are these guys, the ends are parallel to E. You just get, it'd be the magnitude of E, because it's always normal to the surface, times the area of that surface, and that's 2 pi, the radius, how far you are away. It's R. And then just, I'll use, what do I want to use? A length. I'll use a length like that. This is the length of your cylinder. If you want, you can call it capital L. Right? And by Gauss's law, that integral is just equal to the charge inside, which I'll call Q, divided by epsilon naught. And what I wanted was a charge per unit length, but that would just be this Q inside your box divided by the length of that box. Right? And so that's, if you want to, you could then take this, push it down there, take that, push it up there. And so the charge per unit length is the charge divided by the length, which is just 2 pi, R, the magnitude of the electric field, which is given at a certain distance, and then times epsilon naught. Right? So the other way to have solved this was to remember that for a wire, the magnitude of the electric field is the charge per unit length divided by 2 pi R epsilon naught. That's all that we've just used or shown here from Gauss's law. Right? It's the same result. This is just same thing. All right, so this was 2 pi times, was it 0.01 meters? 0.01 meters, and I said this was 5 times 10 to the fourth volts per meter, and then I have to multiply by 8.85. And that's times 10 to the minus 12. And again, epsilon naught is given on the front of the exam. And as long as I got these in meters and volts per meters, I don't have to worry about the fact that this guy is, what is it, Coulomb squared over Newton meter squared. Everything will come out correctly in KS units. In this case, I got about, let's see, I got lambda, it's about 2.8, it looks like, if I can read my writing here, times 10 to the minus 10, and that would be coulombs per meter. That's the charge per length. So this was an application of Gauss's law for one of the three simple cases. We did a point charge, we did a line charge, that's this one, and we did planes, right? And those are, again, if you don't remember them, you can get them by remembering these surfaces and applying Gauss's law. And the only thing it's even remotely tricky is knowing that that's the area of a cylinder with radius R and length, length L. It's just circumference times length. Any questions on that one? All right, the next one is a little bit harder. It says, what is the electric field at position AAA, where A is 1 meter? Unless you'll work to get credit. And hint, these are vectors. Well, there are vectors and there are scalars. And this, actually, by the way, is, of course, a vector because they ask for the field. And in this particular case, if you've got this first part, or you remember this result, you already know the magnitude of the electric field. You can plug in, you just found lambda, and you can plug in for lambda. I said this was 1 meter, and of course everything else. The other way is to notice that I gave you the field at 1 centimeter, it's 5 times 10 to the fourth, and I'm asking for the field at 1 meter. That's 100 times further away, right? So it's, I said at 1 centimeter was 5 times 10 to the fourth, so that must mean the magnitude if I'm 100 times further away, must be how much? 500, right, volts per meter. What's that? Right. All right, so we know the magnitude. That's not hard to get if you know that it falls off like 1 over the distance. But what's the direction? Oh, and there's one other thing that's tricky about it, right? I said it was A that was 1 meter, right? All right, so let's work it out. This is actually not quite right. Lambda over 2 pi epsilon naught r, and we are at a position which I said was A, comma A, comma A. Right, where that's 1 meter, 1 meter, 1 meter, because A was 1 meter. Is that right? See? 1 meter, 1 meter, 1 meter. It says you're at the position, well, X is AAA, where A is 1 meter, so this is 1, 1. Okay? So in this expression, what is that distance there, by the way, actually? What does that refer to?
Magnitude of it?
The magnitude? Not quite. This is where it's a little bit tricky. This is why it's harder. So if we were at some location up here, like here's my origin, right? And so maybe 1 meter, 1 meter, 1 meter is up here, right? What that is referring to actually for a wire is your distance from the wire. It doesn't care about the z. It doesn't care how far along the wire you are. Okay? If you go through the analysis, the only thing that's important is your distance. It's a perpendicular distance. So it's actually call it it's this r up here, not the length of the position vector. Right? So in fact, this radius down here, the way I wrote it a little bit better in class was this is lambda over the square root of, get the 2 pi epsilon naughts in there. 2 pi epsilon naught, it would be the square root of the x component squared plus the y component squared. And it doesn't care how far along the wire you are. It's the perpendicular distance. And so that would be square root of 1 plus 1, that's the square root of 2 meters, down there. Not 1 meter or the square root of 3 meters. Right? And then the direction is also a little bit trickier because this of course is just the magnitude of the electric. Which way is it pointing? Which way is the electric field pointing?
Normally outwards?
It points, you might say, in the normal direction, right? So if I'm at this location, it points this way. My origin is down here, this is 1, 1, 1 here. And which way is that? And if I'm at that location, which way is this? Well, it's something with no z component. Z is this way, it always points perpendicular to the wire. It's got no z component, but it has the same direction as the x component. Which way is that? Say the points, and it's actually 1, 1, no z component. Of course, that's not normalized, right? So if you wanted to, you could say it points in this direction, but if you wanted to normalize that to 1, so it's a unit vector, you divide by the square root of 2. You divide by its length. So that's, again, this is a harder one because now you'd say I'm going to calculate this, and I multiply by this vector. Right? So first thing is to figure out the magnitude of the vector, and then figure out its direction. And this is a hard one because I threw in a z component there also. So this